Right, well, I've got a message from Camilla that we can start, so fantastic. For those of you who don't know me, I'm Kevin Brooks. I guess I'm here because I'm involved with the South African Council of Automation and Control, and I'll be giving part of the talk today. The webinar is co-hosted by the South African Institute for Mining and Metallurgy and the South African Council of Automation and Control. It's a natural partnership for us to work together. We've been trying to get some talks going. We had one previously on some robotic stuff, and today this talk on model predictive control, which will be given by Dr. Loutjie, Coetzee, and myself. So from my side, thanks very much to SAIMM, who've done the majority of the organization for this. And as ever, thanks to SACAC for the opportunities they give us to talk about control. So I'm going to move straight in to introduce Loutjie, who will be giving the first part of this talk. Loutjie got his BEng, there he is, LECEng in 2003, and PhD in robust nonlinear model predictive control of a closed milling circuit in 2009, both from the University of Pretoria. He started work at Mintech in 2008 with the main purpose to develop the robust nonlinear model predictive controller into an industrial applicable controller and commercialize it. The so-called RNMPC has been successfully commercialized in the minerals processing space on milling circuits, thickeners, DMS, leaching, and even on underground mine cooling systems. And not just in South Africa, it's installed in many countries worldwide: Australia, USA, Chile, Mexico, Sweden, to name a few. Loutjie's been involved with the South African Council of Automation and Control as part of Mintech since 2008, and more recently started serving on the executive committee of SACAC, and he is currently the vice president of SACAC. The title of his presentation today is Optimizing Control of a Grinding Circuit to Improve Flotation Performance. So with that, over to you, Loutjie.
Thank you very much, Kevin, for that introduction. Let me just quickly share my screen. Okay. Can everybody see my screen? I just want to see if I can move. Okay, so welcome everyone to this session on models for control and optimization. And I think me and Kevin independently developed our talks, but I think it is actually a good fit together. So just apologies, we are starting load shedding right now, but hopefully our generators will kick in. And so I'll be talking about grinding control or grinding circuit control with the aim of improving flotation performance. And then Kevin will look at a case study on flotation control directly. Okay, so for my part of the talk, I'll be basically starting off with the primary milling circuit, introducing that, look a bit at linear versus nonlinear control. Just this is a bit more theoretical and justification for that. And then just look at where non-linearities can be introduced. So phenomenological models or first principle models and how that can be added as a way to do model predictive control. Then also looking at the economic objective, which typically is nonlinear as well. So because that's ultimately our goal, is can we actually control these circuits economically more viably or more profitably. And then I will quickly just show data from two real world examples. I haven't translated that into dollar terms or rand terms, but I think for people that for background in minerals processing, the benefit will be quite clear to estimate. Okay, so for this talk, I'm going to be focusing on a primary milling circuit. This is a typical circuit in PGMs, in this case a Merensky ore that's being processed by a primary mill that uses hydrocyclones as its is classification. It then goes into a surge tank or a conditioning tank before it feeds into the flotation circuit. So for this case study, or for this example, I'm going to be looking at what can we do with this specific milling circuit in order to improve the feed to the flotation, having therefore better flotation performance. So just quickly, I'm going to run through the circuit. So we assume we have a silo with 2 feeders that feed into a conveyor belt, a weightometer that measures the feed rate into the mill. On the mill, we have the mass or the load, and we have the power as a measurement. It discharges into a discharge sump. We can add some water. We measure the level. We have the pump, and we can actually measure the density, the flow rate, and the pressure going to the hydrocyclones. In this case, I'm also assuming the hydrocyclones is a cluster of 8 cyclones, which can be switched online. The underflow goes back into the mill, overflow goes to the conditioning tank. Here we also have a water addition that we can use. There's another level that we can measure, and we have the density and the flow that we pump into the primary roughers of the flotation circuit. Okay, so when we talk about models, typically in the model predictive case, we usually refer to dynamic semi-empirical models or even purely empirical models. So what that means is that we will do perturbations, we will make changes to the plant, step a valve, step a pump, step the feed rate, and we will see how the process responds. And then we will fit some sort of mathematical representation or model to capture those dynamics. So in this case, once we made a step change, we can see that the control variable has increased and then settles out at some steady state value. There's some dead time at the beginning, and there's some transition time or dynamics that's happening here. And we can represent it in this format as a semi-empirical model. So we can do this modeling either by hand, or we can use some automated tools. So if the problem gets bigger, becomes more efficient to actually use automated tools that then does the perturbation for you. So you don't need to pay an engineer to sit at the plant and say, step up, step down, look at all the variables. But the automated system can do that. That gives you results in a short amount of time and also with less cost. And once you get this data, we can, in this case, look at it in the frequency domain and see what variables responded. So we, in this case, perturbed the sump level set point. We can see that the sump level actually responded as we would have expected. We can see that the screen feed density actually responded, but there was no respondence on the rougher density, surge tank level, the power draw of the mill, again, as we would have expected. We can see nothing on the solids feed rate. We can see the water addition changed. Discharge pump didn't change, rougher feed flow rate didn't change. Also the water addition to the surge tank didn't change. So we can get a lot of information about how does the process respond to certain perturbations that's made, and we can draw some conclusions about what variables interact with and what variables are independent of each other. And when we're done with this exercise, we will get to a matrix of models that will say, okay, if we change the solids feed into the mill, the volume of the mill will change. With this dynamic, we'll get the mill discharge, or the cyclone feed density will change using this dynamic. Similarly, if we look at the water addition into the sump level will change. We will get, again, the density changing with this dynamic, and we'll even see the rougher feed density changing with this dynamic. And so we can go through all the manipulated variables versus controlled variables and see what is the interactions between them, what is the correspondence, and how does the dynamics look. And we will use our process knowledge in this case to evaluate, does this make sense, does it not make sense, is the direction correct, is the model structure correct, is the type of dynamics what we expect. So once we have that, we can then configure our model predictive controller to do regulatory control. So basically, what we mean by that is we control to some predefined set points, operating points that the operators want us to control. And in this case, I'm just going to run this video. We can see that this is the reason model predictive control is advanced process control is that it's multivariable. And as its name also implies, it's predictive. So this part of the graph is showing the predictions using the mathematical models of what the process is going to be doing. And on the left-hand side, we can see the actual behavior of the plant. So what we've done here is we've lowered the limit of the water into the surge tank. And because we've done that, it is trying to lower the water here, increase it on the sump side. But because it's doing that, the addition of extra water into the sump wants to push up the level. So it is pushing up the pump to compensate for that. And because it's pushing up the pump, the pressure wants to go up. And so it needs to make provision for and to make sure the pressure won't exceed the limits. It also has to check that the flow rates won't exceed the limits. And we can see that it moves all the variables at the same time because there's interaction. So we just don't want, in this case, we might want to just change the density on the cyclone side, but there's not just the density that's changing when we change the water, the volume is also changing. So in this case, what we've done is we've changed the density target to the flotations from 1.32 to 1.35. And what it's doing now, it's saying, okay, I need to reduce water, but as I reduce water, the volume needs to drop. But because the volume is dropping, the pressure also wants to drop, but we actually want to keep the pressure up for good classification. So it's actually closing a cyclone in the process in order to keep the pressure close to its upper limit. And all of these changes, we can see almost all the manipulated variables are changing at the same time. And it is doing that so that it can reject the effect, say, on sump level. So there's minimal effect on sump level. It's trying to minimize the impact on flow to the roughers. And it will then try, in this case, there's actually some optimization in there as well. So it's trying to say, okay, while keeping this this density at target, can I maximize the tonnage through the mill so that I can get some optimum economic performance? So I'll start speaking about optimization now, but I hope that this demonstration just gives you a bit of an idea of the regulatory control, multivariable regulatory control capability that MPC brings. So there's a few benefits. It can deal with the interactions. As I said, if we change water for density, there's also a volumetric effect. If I change the feed rate to the mill, there's density and volume effects downstream that needs to be handled. Also, it's one of the few control strategies that can actually deal with constraints on the control variables. So if I know that I have a volume limit downstream, that because my flotation can only handle a certain volume due to residence time reasons, then it can back calculate from that constraint all the way to what is the optimum feed rate that will not exceed that constraint. So that is the benefit. So it can handle these interactions, it can handle constraints. It is predictive, so it knows any change that is going to make the process, how is that going to affect the process. Okay, so let's move on. So as I said, we get these models, and in our case, the models are translated into ordinary differential equations because it also has to make provision for nonlinearity or nonlinear models to be represented. And we use state space representation. So we have the states, and the states can be real or it can be just a mathematical construct. So if it's real, it might be something like the sump level that's being represented by a state. And the state is how is where the dynamics are happening. So we can say the sump level is increasing. The rate of increase in the sump level is being described by the mathematics on the right-hand side of the equation that will say, okay, this is how the rate of change will happen because of the pump speed, because of the water addition into the sump. And then the controller will know, okay, if I balance the pump speed, the flow out of the sump versus the flow into the sump, then I will get to a steady state sump level as an example. So it looks at this whole model, it derives all of its interactions for different variables from this and uses it in its prediction in order to calculate the optimum control moves it needs to implement on the plant. Okay, so linear control, this is actually more a statement, is suitable for most control problems. And the reason is that we typically operating around a fixed operating point. And if you look at that behavior, if I'm operating around a fixed operating point or in a small operating region, then the models can typically be linearized and still give a very good approximation of the dynamics of the behavior of the plant. Non-linear control is more common in batch processes because there we start at one operating point and we want to move the process to a completely different point, and it might go through different behaviors as we move the process from one state to another. And but also we can see that non-linear control can start to have an impact when we're doing optimization. So in this case, we say we can add nonlinearities, and that can be due to having phenomenological models or first principle model components in our models that can describe the changes in steady state as we move from one operating point to another more accurately, with just some parameters that needs to be fitted to a specific plant. So we will only add it where it makes sense, and I will give some examples of where it might make sense in the milling context. It is useful for lights out control and whole process optimization, propagating backwards where the process to operate over a large operating range. So say so what I'm describing here is Industry 4.0. It's all about doing very flexible production or very flexible manufacturing. So the requirements of the clients change and you have to set up your manufacturing to match. And if we expand that idea even further back, if the industries that buy our raw materials change their requirements on the fly, it might also eventually come through to mining that says, okay, the need goes up and down depending on what orders are placed, affecting the price, and also then where's the optimum point to operate our mines to cater for the price and volume requirements coming from the downstream industries. But it is a lot more difficult to get and to maintain nonlinear models than linear ones. So in most practical cases, even in our case, we use linear control for regulatory control. And we're only really investigating it for optimization where it makes sense. So if we go back to our milling circuit, where is typical nonlinearities that is present? So the first one is the mill. The mill has some nonlinear steady state behavior depending on the volumetric filling. So if I fill up the mill, if it's on the underloaded side, it will behave in a certain way. If it's on the overloaded side, it will behave differently from in a steady state. And I'll explain that a bit more. The hydrocyclones is also a point of, especially if it's a cluster, it also has some nonlinearities, specifically discontinuities that is present in the model. And then if we're looking at the interface between milling and flotation, if we want to reduce the flotation problem down to a simple metric, that is also quite a nonlinear process in itself. And I'll explain each of these 3 points in the next few slides. So if we just look at the volumetric filling, or as a proxy, the mass of the mill compared to the throughput, there's a well-known throughput curve that we can get. So here's an example of how we can linearize. So if we limit the application of the model between 15 and 30% volumetric filling, we can easily approximate this parabola as a linear line, so as basically a linear model with a fixed gain. If we want to widen the limits, however, we start to get changing behavior, where on this side, if I increase the volumetric filling, the throughput goes up. If I'm in the middle, there's almost no change. And if I go on the overloaded side, if I increase the volumetric filling, the throughput actually goes down. So if I'm still applying a linear model on this side that says a volumetric filling will increase the feed rate and the feed rate starts to drop off, it will say, oh, okay, I must just push up the volumetric filling some more, worsening the problem because it's not aware that there's a change in the steady state behavior happening here. So if we bring in mill speed into the mix as well and volumetric filling, we get this three-dimensional curve in terms of mill throughput. So we can see it's a three-dimensional surface that I need to use for optimizing my steady state behavior. If I look at mill power rather than throughput, then I can see it's also a 3D surface, but it looks very different compared to the throughput one. So there's two different surfaces with two different peaks and two different behaviors that needs to be combined if I'm looking at the steady state behavior of the mill. And that's just a very simplified looking at two parameters of the mill. There's even more when we look at densities or rheology, if we look at ball loading, that starts to play a role in terms of the mill behavior. And also, we look at the speed, it is the impact position of the toe that can also play a role. So if you're undershooting or overshooting that toe position, it can also have a drastic change in behavior, increased liner wear, increased ball wear, but also reduction in throughput. So there's a lot of factors that just can be described around the mill alone in terms of steady state behavior. If we move on to the cyclone clusters, so say we work between 6, 7, and 8 cyclones, then we have the flow rate to the cyclone increasing. That gives us an increase in pressure until we hit the maximum limit on pressure. If we open a cyclone, then we have a drop off in pressure. We have a drop off in pump speed, even though we're keeping the flow constant. So that's the reason for that, is that it's now easier. There's less resistance to flow. So we don't have to run the pump as hard in order to maintain the same flow rate. And then again, it moves up. If we open a cyclone, it drops off, the pump drops off, and then it starts moving up again. So these discontinuities is also a form of nonlinear behavior. And what's also in this case present is discrete. It's discrete numbers. So we can't have 6.2 cyclones or 6.3 cyclones open. So we can't do continuous controls, either 6 or 7 as a discrete number. Then if we start looking at the net smelter return, we can look at the transport cost for transporting the concentrate grade to the smelters. We have the processing cost to say how much does it cost to get a certain concentrate grade of metal. So we can look at what is the metal value. So as the grade goes up, the metal value goes down because we have less recovery. And then if we combine these three curves together, we get the net smelter return, and we can see that there's some optimum concentrate grade that will give us the best value per cost in terms of metal. And that is our ultimate economic objective for a concentrator, let's say milling and flotation, is to optimize this net smelter value. Then we can have a look at what does a low metal price or a high metal price impact have on this net smelter return. So we can see at a high metal price, we actually want to run at a higher concentrate grade, at the lower metal price, a lower concentrate grade in order to get the optimum. So there's impact in terms of the metal price. We can even say as all grades change, this will have a movement in the optimum point of the curves as well. So here's just from Will's minerals processing technology, where I got this information from, showing the grinding costs and the net smelter return. And if you combine the grinding cost with the net smelter return to get a net smelter return grinding cost curve, which will have a different optimum. So where we might say purely on net smelter return is lying there, but if we take grinding costs into consideration, the optimum actually shifts to this point. Then we also have recovery of metal to concentrate versus time, and the recovery versus concentrate grade curves on the flotation side, all being nonlinear curves. We have the particle size to rate constant, the cumulative grade in rougher flotation versus time. So the grade, as longer we're floating, the higher residence time, the lower the grade, because we're starting to recover again. So all of these things on nonlinearity. So what we're trying to do is, can we move the recovery and the grade curve up using control? So not just stick on one grade recovery curve, but can we actually move this curve in an optimal direction? So getting a good grade, but at a better recovery. Or maintain a certain recovery at a better grade. That is the ideal that we want to achieve. So what we can do is for this simulation, so I've just drawn up a very, very simple model of the flotation circuit, where I say that the two input variables going to the flotation is the flow rate and the density. I haven't even included grind, and say that that maps to some sort of concentrate grade on the flotation. So at the moment, I'm not looking at doing any control on the flotation. I assume that the control that's in there, if I can get the density and the flow at a certain point, I will get a certain grade from my flotation. And then we have the parabolas that I've shown earlier for the net smelter return, for transport cost, processing cost, and metal value. And then I combine these, so I get the net smelter return. I'm then adding a second objective where I say I'm just looking at, can we push throughput through the milling circuit as high as possible while keeping within certain constraints in terms of density and flow. And then I'm actually combining the two together, because the net smelter return gives me the maximum value per unit processed. So if I take that maximum value per unit process and multiply it by the number of units that I can produce, what type of performance will I get? So if I'm looking at these three, so this is just some of the nonlinear models that I've added. I'm not going to spend some time on this. This is the how the objective function has been defined inside the controller. So we have the grade, the transport cost, processing cost, metal value, net smelter return, solid feed rate, and I haven't updated it for that combined net smelter return solid feed rate here. But that we describe explicitly in the controller and say, okay, optimize economic depending on which of these objective functions I activate. So I'll get to those results in a moment. Another thing that can start to play a role, I don't think we're there yet, but as electricity prices keep on going up, we also get the time of day value for electricity. So if we get the normal time, we get the peak times rate, and then we get the off-peak time rates. And at some point, they might actually start to affect the economics of the grinding circuit, where it might actually be more optimum to move the operating point of the milling circuit to respond to these time of day charges in terms of electricity. There might also be some peak energy demand that can be placed on the milling circuit from Eskom in these peak hours as well, that you also have to adhere to. So, so the controllers can also take this into account in terms of what is the electricity price that we know up front, and also what is the constraints of electricity that's available to the milling circuit. So we'll then define one controller that looks at this whole milling circuit in one go, understanding all the interactions, understanding the economics as we've just described it, and we can say control, regulate it, and then also calculate where to regulate it to. So what is the right density? What is the right flow rate? What is the right mill volume? What is the right feed rate to the mill that will give us the best economic benefit? So we're no longer dependent on the metallurgist or the operator to define those values, trying to figure out on a daily basis where that should be. But the controller can actually, using all the sensors available to it, as well as the economic objective, then start to calculate that in real time as things change. So what we can see in this graph is just if we activate the limit, say the peak times on the milling circuit, where we say, okay, you can use 11 megawatts most of the time, but during peak time you're limited to 7.5 megawatts. We can see the real power draw of the mill dropping and then recovering, dropping, recovering as it adheres to this limit, and it will change the operating point of the mill in order to achieve this. So again, the solids feed rate as well, because we're dropping the power, we might have to drop the feed rate. And because of the feed rate, it will have density and flow implications. So it will also need to take that into account to find out what is the most economic point to operate here, and that is the most economic point during the other tariff times of the milling circuit. So this just shows again the pressure. So what it's doing is it's actually closing the cyclones, because it knows due to the drop in feed rate, there's less volume, but I do want to keep my pressure up in order to get a good grind and in order to get a good separation in the cyclones. So it is closing the cyclones to compensate for that change in volume, and then it's reopening them as soon as the higher volume periods kick in. So cyclone free flow rate, mill speed. So we can see how it's doing that that reduction in power. It is slowing down the mill during the peak periods and then speeding it up in order to get that reduction in power in the mill. And it's also changing the volume of the mill in order to compensate for the lower speed, still giving enough volume to get the grinding that we need. So it knows that if I change the speed, it has impact on the volume that will affect the grind, so it makes provision for that. So just another view of the power to solids feed rate. So I want to get to this. So let's look at the combined, or let's look at the economic objective. So here we can say, what is the revenue in rand? And this is millions of rand when we have a certain feed rate, tonnage an hour, and a certain grade. If we combine those net smelter return with feed rate type of objectives, and we get this 3D surface. So now we can say, okay, if we just target net smelter return as our optimum, we can say we end up at this point for revenue, because it doesn't take the feed rate into account. So it optimizes net smelter return at all costs, even feed rate. Or we can say, okay, let's look at the more traditional metric, which is let's maximize feed rate subject to some limitations on the density and flow rate. And we definitely get a higher feed tonnage, but we're not necessarily getting the best rand value. When we actually combine these two, then we move up the curve. So we're not losing that much feed rate. We're not getting exactly the same level of net smelter return, but the combination is actually optimal. So we're getting the best rand value at the end of the day, and that is what we are interested in. So we can see that the controller can do these trade-offs to say, okay, if I need to sacrifice net smelter return, the value per unit that we can get, and we have to sacrifice the tonnage slightly, the overall rand value is actually better. And this is the high metal value case. So if we go to the low metal value case, we can see the surface changing quite considerably. And we can see that these points are actually moving apart quite wide. So in this case, if I'm actually targeting purely net smelter return or solids feed rate, I'm actually very far away from the optimum rand value. So in the low metal case, the benefits of targeting a combined net smelter return or trade-off between net smelter return and solids feed rate has a much bigger impact in terms of the economies versus just looking at either one of these two in isolation. So this is just a bar graph to highlight the same thing. So we can see in the high metal case, there's not that much difference, maybe between the solids feed rate approach and the combined net smelter return solids feed rate approach. But if we look at low metal price, there's quite a huge difference. Yeah, it's actually interesting that the net smelter return does better than targeting solids feed rate. But if we combine both, there's quite a big difference in that. Okay, so you can say, but this is all simulations. So does this really apply to the real world or real milling circuits? And I'm just going to show two case studies. So I've hidden the values just to anonymize the client and the values. But if we look at, this is just a very simple comparison between the density, cyclone feed density, and the recoveries that we see in the flotation circuit. So we can see if we dilute the feed to the flotation too much, there's quite a steep drop off in terms of the flotation recovery. So as I show, from the peak year to this bucket, there's a 3.7% drop off in recoveries by just operating at the wrong density. So targeting that right density is very important. And even if you go to higher density, then you will also see a drop off there. This might be a bit disingenuous to display it this way, because it doesn't mean we can actually increase the recoveries by 3.7%, because over the time period, there's a certain amount of time that the milling circuit was operating in each of these buckets. So the real improvement is basically, if it's 20% of the time in this poor performing bucket, and we can move it out of that, then we will get 20% of that 3.7% improvement in terms of recoveries. In this case, we're actually using a particle size soft sensor, and we were looking at if we were targeting a certain grind at P80 from the milling circuit, what would the effect be on zinc recovery and lead recovery? And again, I've just anonymized it. But again, we can see from the lowest value, I'm excluding this one. If I look from this one till the peak year, there's a 0.5% improvement. And here as well, from this sections year to year, there's about a 1% improvement in the recoveries on the flotation. So just looking at your milling control, making sure it operates in the right regions, without even looking at flotation control, we can already start to get some significant improvements. It might not sound like much if we say this one will probably be 0.2 to 0.3% improvement if we just look at the time in the different buckets. But 0.3% improvement is still enough to pay for these type of installations in a year or so. So it's still enough money that it's worthwhile for that type of improvement to look at it. Okay, so just some of the references that I have. So yeah, that concludes my talk. Thank you, everyone. I think we will have our Q&A at the end, Kevin, or what is the plan? I assume after you've spoken, then we will do our Q&A.
That's correct, yeah.
Okay, so it's now my pleasure to introduce Dr. Kevin Brooks, that will do the next part of this talk. So Kevin obtained his BSc Chemical Engineering in 1980 and his PhD in 1986, both from the University of Witwatersrand, where he lectured until 1990. He joined Honeywell High-Spec Solutions in 1995, working in dynamic modeling and advanced process control and optimization. He was appointed engineering lead for APC and led projects in both South Africa and Europe, and in particular Eastern Europe. In 2007, Kevin joined Blue ASP, the AspenTech distributor for South Africa, as a principal consultant and later chief engineer. In his capacity, he performed projects in ethylene, fuel gas network optimization, and together with Anglo Platinum, pioneered the application of APC in the mining industry. In August 2021, he formed APC Smart to mentor, train, and consult in APC. He holds an adjunct visiting professorship with WITS, where he also co-supervising some 10 graduate students, several of which are working in flotation modeling. He was president of SACAC in 2013 and 2014, and held his position for 2 years, a period which included the hosting of the very successful IFAC World Congress in Cape Town. You are talking on, sorry, I've now lost our title there, but
I'll share the screen now.
Yeah, so basically the topic of our webinar. So.
Gosh, thanks so much, Loki. Thanks a lot. People will take questions. They'll be moderated by Anthony Higginson, and we'll take questions at the end. So thanks, Loki, for that really interesting look at grinding. And as Loki said, it's somewhat fortuitously, I'm going to talk mainly about flotation. So this is my agenda. I might shoot through some of the early stuff on defining what APC is. Loki's done some of that already, and really get to the heart of MPC in flotation. So just very quickly, I mean, why can we do what we do now? It's because of the advent of digital control in the mid-70s. Before that, we had pneumatics. They worked very well. There were some very clever things done, but the kind of things Loki's just talked about, even 15 years ago, were difficult to do. So it's the digital control that's allowed us now to apply these algorithms. What do we mean by APC? APC is many things to many people, but I include in it intermediate regulatory controls, which can be things you can build in a DCS typically, or a PLC. This, for instance, is the cross-limiting burner controls for a boiler. A lot of you may have met fuzzy logic. If you've got a Samsung washing machine, you apparently have met fuzzy logic, which is one way of doing a sort of rule-based control, and is quite popular. And there are many companies supplying that. But as Loki's eloquently said, the model predictive control gives us the multivariable element and gives us the predictive element, and includes optimization as a mathematically rigorous function. Whether it be linear, nonlinear, doesn't matter. The point is it's built in. And I think experience has shown that trying to do that in fuzzy and rules-based systems is tricky. Okay, Loki too has talked about the models. I'm not going to go over this at all. We have the empirical models, we have the non-empirical models, we have linear, we have nonlinear. That's up to you. I've largely worked in linear empirical modeling, and that's what I'm going to talk about today. And this, my real point about all of what we do, and again, Loki's talked about that, is that we have a rigorous objective function that we're optimizing either at steady state, like this one, or along the trajectory. That's also an optimization problem. Okay. With MPC, we can estimate benefits upfront based on improving the control and then optimizing. And we can operate at constraints, which operators typically stay away from. In this particular picture, the constraints are linear, and then you have to operate at a vertex. Okay. Where does it all come from? Well, it comes from our colleagues in oil refining, largely. DMC, the very popular algorithm, was developed by a guy called Charlie Cutler, who was with Shell, as was SMOC, developed by Pascal Marquis, who was at Shell. He was in Europe, Charlie was in America. And then the Honeywell tool, also developed from a variety of packages. And these kind of tools are now standard on in oil refining and petrochemicals. As far back as 2003, Chin and Badgewell did a survey that listed 3,000 applications in refining. So it's a successful technology. They also listed some other industries. I've put some of them, but the one that stands out is that for us, there were 37. So 1%-ish of what there were in oil refining. And we have to ask ourselves why. Why, even in 2003, had this successful technology not infiltrated into the field we work in? Some points that I'm not saying these necessarily are the case, but they could be the case. Mining companies are slow adopters of new technologies, and there used to be, I think, a resistance to the use of modeling as a tool. The belief that complicated solutions get switched off, and that the other kinds of technology I talked about might be more suitable. At admittedly reasonably high initial cost, even though there is acknowledgement that the returns on investment are very fast, almost always less than 6 months. And then ones that I've become more and more interested in, which is that the measurements aren't available and the sensors are noisy. And there's a couple of ways you can address this. You can invent new sensors, and I think we know of companies that are doing that. A lot of image analysis techniques are being used now very successfully. Or you can go the route that Loutjie mentioned of soft sensors, which is also a very satisfactory route, particularly given the uptake in artificial intelligence, machine learning type algorithms that are now available. There may also be the doubts about the use of linear models. Yeah. There's a literature review recently by Rogers, who listed some references and basically was saying that in academia there are some references, but there are not many references in applications. I'm not so sure about this paper because I don't think he caught the stuff that I've published, so he can't be very good. But it looks like either we're not doing the stuff or we're not talking about it much. And yet, as Loutjie's shown, with an example very similar to the one shown here, the modeling that we need and the application is not, in terms of the model predictive control that is done, is not that complicated. So we should be doing more because the benefits are definitely there. Okay, so some areas where in the triple M field, MPC has been used, either where I know it, I did it myself, or I know other people have done it. I'm not going to go over them all, but we've talked about milling. I'm going to talk about flotation. I've done thickeners. Electrowinning is a field that can be used. I know of a jig plant application. I'm particularly interested in solvent extraction. Given the hydrometallurgical routes that people are developing now, this is going to become more important. So I think not only can we do it, in some cases we already know how to do it. So the case study I'm going to give you is the other side of the world. Mount Isa is a plant we worked in. And all the results I'm showing you have been published. There's nothing secret. And we worked on the lead and zinc side. There is a copper plant there as well. It's not close to anywhere, and yeah, in the middle of the outback. So, but for a process control engineer, an interesting place to work. And when it was Xstrata, it's now a Glencore operation, but when it was Xstrata, and subsequently, they've done a lot of work developing new processes. So things you might know, like the Isa mill and the Isa smelt were developed there. And they've done a lot of work commercializing, especially Glencore, the Jamison cell. So the flotation plant that I'm going to look at, well, part of it is a fairly complex one. So it's a lead zinc, as I said, lead zinc operation. They float the lead, then they float the zinc. And there are lots of cells and lots of banks and lots of cyclones and lots of mills. So this was a very interesting project. I'm going to just limit myself to talking about 2 cells because it makes sense. We didn't only do 2 cells, but the real advantage we had there was that the components the compositions are measured online using XRF. So we have X-ray fluorescence analyzers These are sampled analyzers, or they're sampled systems. So you'll get one XRF is measuring more than one stream using sampling, and that has its own challenges. But it does mean that you've got measurements where typically you would normally only have assays from a lab. So if we then do the kind of analysis that Loutjie did as well for the grounding circuit, what are the inputs, what are the outputs, we find that we can manipulate air level and reagents. So we've got the air coming into the two cells, reagents typically at the front, and then the level, in this case, it's one level for two cells. And that we want to control the profiles of air and level, but in particular, we want to control the compositions in the tails and the concentrate. And we've got disturbances to the system, like the feed rate, density, and the compositions of the feed. And in this case, we developed linear dynamic models, purely empirical, as Loutjie mentioned, using automated step test techniques. There's an example of the step tests that we did. So this is air, the two airs, the one level, copper sulfate, which is an activator, and ethyl xanthate collector, which we moved around. You see, we've included some data where the reagents were moving, but the air and level weren't. This is some work that I'm doing together with a colleague on what historical data can we use to develop these models. This is an interesting area. And then here you can see the XRF data. And largely here it was behaving itself. There's a bit of a dropout over there. I did something there to fix it up. But this is quite good data. But in fact, normally it isn't very good. And you have to do some tricky stuff to validate it. And in fact, myself and Margaret Bauer have written a paper on that as well. So this is good data for model analysis. And the model comes out something like this. I'm not going to spend a lot of time on it. Like he's talked about the models, and these unit step responses are the way we show the behavior. See, in this particular way of showing it, the inputs are down the side and the outputs are across the top. So here we've got the effective levels and airs, copper sulfate and the xanthates on the conch and the tails, and then we're controlling the dosages explicitly there, and you can even see the effect of the feed and the zinc in the feed on the dosage. So this way you can do very accurate feed forward control of the dosages when you see something change in the feed. Okay. The control objectives, and yes, it would be great to include the kind of things Loutjie was talking about on the mill. In this case, we hadn't yet done the mill, so we didn't include that. And we had fairly simple objectives, which were to maximize recovery and minimize reagent dosing in this case. These are all subject to the other constraints on the system. So maximize recovery doesn't mean that the grade of the concentrate can be anything at all. There will be a low limit set on that. So you end up with the constraint problem with the vertices that I showed in the previous picture. Okay, some results that have been published. We're looking here at the copper sulfate and the ethyl xanthate, and these are frequency distributions measured before MPC in the dotted lines or the dashed lines, and after with the solid lines. And here's some statistics. And the key one here is that the application of MPC has reduced the standard deviation of this variable by 30%, allowing it to be moved down. And the move down has been 20%. And here, even better, 40% reduction in standard deviation and a nearly 40% improvement in the use of ethyl xanthate. And the financial benefit of this at the time was in the region of $1 million Australian per annum. So a very worthwhile project for Glencore. What do I see as the remaining challenges in the field, apart from getting you guys to do it? We have to look at the instrumentation and the soft sensors. We have to be fussy. Why shouldn't we have as good measures as they have in oil refineries and spaceships? I completely agree that there are some cases where nonlinear responses have to be taken into account. In fact, I have a student, and I believe she's on the call today, doing work on the nonlinear response of the system to reagents. We have to look at the fact that the churn in operators and engineers is very high. So we have to find a way of making our applications self-sustainable. And this isn't just in model predictive control. I think this is in all the software that it's become very popular to apply digital whatevers. But you have to be very careful that these applications are sustainable. Okay. Proving benefits is a bit tough because we're talking, Loutjie said, you know, that these are small recovery benefits and they're worth a lot of money. But how do you prove that you got a small benefit? There's always going to be someone who said, well, I built this, or I did that, or I changed this procedure. So this is a trick to do the post audit in a proper way. I think we have to be aware of the data scientists. This again might be a bit controversial, but I think there are people working in our field now who don't have the domain knowledge, who haven't worked in our field, who don't have the training, and will make promises about what you can do with models. And that's fine. There is some very cool stuff you can do with models. But if you take these models and put them online, you better know what you're doing. So I think we have to work with these people, but not always believe them. We have to be critical, because our map is much more complicated than their map. If you're interested in control, then this map is available for download from the internet, and it's very interesting. We work in a small little area over here somewhere. And I've shot through it because I wanted to leave time for questions. If you have any questions, please feel free to get hold of me, and I'm sure Loutjie is going to say the same. And we will post these slides. I will post these slides, and here's some references to some of the work that I've used in producing this presentation. So thank you very much, and I'm going to hand over to Anthony Higginson. Anthony's a process control lecturer at the University of the Witwatersrand in the School of Chemical and Metallurgical Engineering, and he's just going to moderate the questions for myself and Loutjie today. So over to you, Anthony.
Many thanks, Kevin, and many thanks, Loutjie. Both presentations were incredibly interesting, and it's always good to see concrete examples of things being applied and showing great improvements. We currently don't have any open questions. I see that there's a comment by Roy Irvin in the chat just saying it's an excellent presentation of how the mines should be optimizing their milling circuits as economic and market conditions change. I think that's something that everyone can agree with, that it should be something that everyone is looking at. So if anyone has any questions, please post them in the question and answers tab. because currently we don't have any, which might mean that it was just an incredibly well done presentation. I might actually just ask a quick question in terms of what is the limit of the types of optimization that you could look at in an MPC? Could you look at things like water utilization and environmental emissions as something that you might want to optimize for as well?
Okay.
Yeah, so to answer that, no, there's not really any limits. Anything that you can measure, you can include. I think the challenge becomes that these optimizations are maybe competitive. So say if you want to push production, it might come at the cost of environmental emissions. So you will get some sort of trade-off between the different objectives that you're trying to control. So that needs to be carefully understood when you're designing the economic objective.
Yeah. So the one, I'll take an oil refining example, but I think I could probably turn it into a minerals process example. One of the problems you get is when the one of the costs is occurring over a very long time, as opposed to the shorter times that we do the control. So the example in oil refining is catalyst deactivation. So you get a unit called a platformer. The platform is what makes the high RON petrol for you, the high octane number petrol. And if you just optimize that using the kind of techniques Loutjie and I have discussed here, then you could end up deactivating the catalyst too quickly. Because one of the big costs on an oil refinery is that if you don't have continuous catalyst regeneration, you have to shut the refinery down to change the catalyst in the platformer. So that's a tricky one to manage because of the very long time scale. Now I can imagine, I don't know, Loutjie, if you've ever looked at liner wear, for instance, or even steel ball usage in a grinding circuit, whether that doesn't sort of fall under the same category.
Yeah, so definitely, I think we're looking at the milling with the new sensors that's becoming available, the vibration sensors. You can actually start to say, okay, but I want to. Fortunately, there the optimizations are aligned. So if I'm getting the right impact at the toe, I'm automatically reducing liner wear. I'm automatically reducing ball. So there's no trade-off there. There's actually, all of them are working together. You're getting better grinding at lower specific energy, less liner wear, and less ball consumption. So in that case, there's no trade-off. It all works together. But in other cases, there might actually be trade-offs between the environmental impact versus the production or economic. So unless you put an economic number to it, that you can balance it out in a correct way, it can become tricky.
Yeah. So you've got to understand the scope of what it is you're optimizing. But yes, so I think I mentioned or Loutjie mentioned in the introduction, I've done work in fuel gas optimization, and that's very much associated with emissions control and so on. Plus work I've done on SO2 plants that are associated with the smelters at Rustenburg. So Christine and I did work there. So there's a great scope for energy and emissions as part of what we do.
Thanks. And so we do actually have a few questions now. So Derek LaRue asks, and I think this is probably directed more at Kevin, just in terms of the sensors, is it the responsibility of the plant to do better maintenance, with the manufacturers to build better sensors, or for the control engineers to use the available data better?
Yeah, I think it's all of the above. Certainly, we do see advanced sensors getting installed, and then it's another advanced application, a complicated sensor, and it has to be looked after. I was impressed with Mount Isa, where the XRFs are looked after on a 24-hour basis by a team of metallurgical technicians. So you have to do that. But also, you know, developing new sensors is it's a rife area for academia. It's not normally hugely expensive. It's nowadays there's a lot of software involved, so it's not just hardware. And I think it's something academia can look at. But then yes, we as practitioners must look at this stuff and say, how can we use it? And you know, and use it, but be careful. You only have to ask Boeing what happens if you use a sensor and you're not careful. So it's a terrible example of how you can go wrong. The Boeing 777. Sorry, Boeing 777 Max.
737 Max, yeah.
737 Max, yes. Yeah. So I hope that answers the question, Derek.
Okay, well, the next question is from Keith, who asks you, Kevin, again, that you mentioned in 2003 that the adoption of advanced process control, or MPC, in the M field was about 1%. And what is your current assessment of where the current situation is?
I'd be very surprised if it's grown to more than 10%. I still think we haven't infiltrated the market as much as MPC has infiltrated the market in oil refining and petrochemicals. Still think these points I made, if not all of them, but some of them, are hindering the uptake of the technology.
Okay, and I think the next one is kind of a more general question, so either of you can answer, is what do you see is it's Robert who asks, what do you guys see as the future developments in the field of MPC and NMPC?
Sorry, MPC and what was the second part?
NMPC.
And NMPC. Okay, I'll take my first stab. I think one of the areas that's coming up, or what we're looking at least, is combination of machine learning type of things, neural nets or Bayesian optimization with MPC. So combining those two fields together to get the best of both worlds, if I want to call it that. The reason is, for me, MPC, the models are very well understood. You know exactly what the controller is going to be doing under which conditions. So if you're putting MPC with linear models as a regulatory control, there's no unknowns in terms of what it's going to do. Where the machine learning models are not always as transparent. So you don't always know where it's going to move. But at an optimization layer with the MPC, keeping it within some sort of, keeping it bounded in a safe area, interesting things can start to happen. So I think the combination of the two, especially, as I said, non-linear models are difficult to get and to maintain. So if you have self-learning non-linear models in your machine learning and using that in your optimization in a safe way, that can be quite an interesting field that develops going forward.
Yep, I almost would have said the same thing. I'm going to add one field that is allied that I'm working in, and that's, we get asked a lot, why can't we use the historical data to develop these models? Why do you have to come and do these tests? And it's a good question. So together with a colleague in Germany, Yuri Schardt, in fact, he's done most of the work. We're looking at methods for partitioning historical data into chunks where we can use it to get the models, and whether it be linear or nonlinear shouldn't matter, in fact, because the chunks should be sufficiently similar that one model should fit them. So if you had 5 chunks and it turned out that you had 5 different models to fit them, then that would be an indication that your system's nonlinear. But unless you've defined the chunks, then you can't do that. And actually, we're writing software, so the algorithms are available. And the hard part at the moment is the is the graphical user interface to make these things usable by anybody, and that's an active area of research. And hopefully, even if it's just to build what we call the seed models, which is the first model you need before you auto test, that would be, I think, a great advantage in the implementation of these things. But I think there are other advantages as well.
Okay, I think the next question is for you, Loutjie, from Eduardo, who asks that in your model you had about 12 states which capture all the processes. So computationally speaking, are you able to get away with a relatively small DCS or even a PLC that has the MPC embedded in it?
We haven't done it in a DCS or a PLC. What we have done is put it on a Raspberry Pi that seems to be running without an issue, that type of controller in real time. So within like 100 milliseconds, it could solve the problem. So yeah, I think the low-end hardware is definitely getting more and more capable to the point where these things can run in real time on them.
Okay, and I think the next question.
If that's Eduardo, if that's the Eduardo I think it is, then he's got up very early in the morning to listen to us, because he's in British Columbia. So if it is him, thanks for attending.
Yes, it was Eduardo Poupard. I hope I'm pronouncing that right.
No, then it's a different Eduardo.
Okay, the next question is from Derek again, who's asking, have you encountered plants where they use mineralogical data from the mined ore to adapt their operating conditions? For example, slow the mill speed for hard ore, and then or change the reagent addition for a change in ore type.
Okay.
Yeah, so I think definitely there is plants that do it. I think one of our current big clients is exactly doing that, and the data that I've shown you there is actually a agglomeration of different ores, and they were specifically commenting they want to refine it to the different ores that they're processing, because they know mineralogy changes, so it might be finer grind in certain cases, coarser in other cases, slower feed rates, higher feed rates. So yeah, definitely they do want to do it. I don't know if they actively always doing it, but they want the control systems to allow them to do that type of work more effectively.
Yeah, my only input, Derek, there is as I said, the dosages are being manipulated according to measured feed compositions, but that is the measurement is of the flotation feed, not the mill feed. So, and that's probably all you need to do. So in that particular case, we're not doing anything that from the mill to the flotation, although we looked at the P80 as a potential disturbance, we just couldn't get the models.
Yeah, so I think maybe to answer the question is that ideally, if you have those online measurements and you can actually see how the flotation responds, you can feed it back as a target to P80 and densities, and eliminate that involvement of the metallurgist to actually have to figure that out or change that manually.
Well, I think the penultimate question then, unless somebody wants to get in at the last minute, we've got James Robbenheimer, who asks, are there currently any plants where all the controllers from the mill to the smelter work to optimize a single objective function?
Not in my experience, no. But that is the ideal that you want to work to. The reason it's not is to a large extent, in our experience, a lack of instruments. So you are dependent, where there's a lack of instruments, on human input to make up for that at the moment.
Yep, that's the whole answer.
Okay, well, we've got 3 more questions now. I had a couple more. The first is from an anonymous attendee. And do you think that MPC model identification from step testing offline using first principles dynamic simulations is an alternative to historical data?
My question for the question would be, how do you know that that nonlinear model is actually representative of the real plant? So at some point you would have had to fit that first principles model, because there will still be some empirical factors that needs to be fitted, and then you can do a step test of that one to get the models. But you still have to fit the nonlinear model to the actual plant.
Yep. So that approach is becoming popular with the reinforcement learning people who build a simulation and then let their agents loose on it. And I guess that's only because they're scared they're going to break the plant if they let their RL system work on the plant.
So if we say, like, combine Kevin's research with historical data and maybe machine learning that fits a black box model that we don't know, you can then go and step that black box model to get your linear dynamic models, which you can then interrogate. So that is a possibility, but again, you need to have some certainty that your black box model is a good representation of your plant, and that's always where it becomes tricky. If that one is not good, then everything else derived from it is not going to be good.
Okay, now we've got the penultimate question again from Keith Mutambira, asking Loutjie and Kevin, do you see much of a successful application of machine learning techniques with sufficient skepticism when it comes to producing nonlinear models, as opposed to machine learning as the controller?
Yeah, we are looking at that. I think internally at Mintek we're looking at, because you get model-based machine learning where it actually fits a model that you can interrogate, or even using machine learning to update the model of your MPC by tweaking the parameters. So that we do see can be a possibility. The other one can be actually a model-less optimization technique that we're also looking at and doing, because if the model is too much variable because of factors changing that you don't measure, then a model-less type of adaptive control from machine learning is also a possibility. But again, as I say, that will most likely run at the optimization phase, not at the regulatory phase, just for safety reasons.
So I may have been a bit cynical about AI and ML, but I'm not. I've even got a student looking at this reinforcement learning to see what we can do in what's called a distributed MPC problem. So I'm sure it's coming. It may be viable while Loutjie's still doing this stuff, probably not while I'm still doing this stuff. So
yeah, so I think
it's for a next generation.
I think our skepticism from me and Kevin comes from, if it's people that comes from the computer science, because that's where these things are developed, coming from that background without any domain knowledge. You're saying, I just need the data, I don't need any understanding of the process to make this work. So that's where people are going to get burned. So even for MPC, to make it work properly, there's a lot of domain knowledge in terms of specifically the processes that we apply to and making sure the models are rational. But otherwise, again, if you just let the auto modeler loose and getting any models and say, oh, that's good enough, and apply it, you're going to burn yourself, even with MPC. So domain knowledge together with machine learning knowledge and making sure there's sufficient way to validate the models is the important thing. So the technology itself, there's nothing wrong with it. You need to make sure that it's combined with proper, I would say, proper domain knowledge and interrogation and validation.
Okay, and I think then to bring things to a close, we've have a final question from Roy Irvin, who says that in an operating mine, there's a lot of grade control sampling. So how much additional work would there be to do metallurgical control sampling, as then you would have more up-to-date data to work from? And would this be advantageous to your goals?
Yes. Yeah. More samples, the better. So if we're not going to go online analysis, then we need to look very carefully at the sampling and what we can do with it. And there are some sampling kind of paradigms that are not very helpful if you want to do online control. And one of them is the cumulative average sample over a shift. That really doesn't help us very much. So one of the things I'm quite interested in is we understand why the plant might want that sample, but can we do something to cut samples at a higher frequency for the soft sensors? And that would be an alternative to the admittedly expensive online analyzers.
Yeah, so with that, I think the questions have come to an end. So thank you very much.
Thanks, Anthony. Thanks, everybody.
Yeah, thank you, everyone. Have a good afternoon.
Yep.
Thanks, Kevin. Thanks, Loutjie.
Thanks, Camilla. Cheerio.
Bye-bye.